Hi, my name is Jeff Lund. I'm a geologist, and I represent two organizations, the Houston Geological Society and the Society of Independent Professional Earth Scientists. And we have an outreach program to teach and communicate geology to high school students and middle school students. We're going to use a map today to discuss geology. The map I have here, it was created by the United States Geological Survey, and it's a geologic map of the lower 48. The colors actually represent the ages of the rocks in the bedrock. And we'll be talking about four areas that are particularly interesting: the Grand Canyon in northwestern Arizona, the Snake River Plain in Idaho. Then we'll talk about the Llano Uplift in central Texas, near Austin, Texas. And then we'll go up to New England, and we'll talk about the effect of the last ice age and how it's affected the geology that we see in New England. Well, first of all, let's discuss what is earth science. Earth science has many different aspects: oceanography, meteorology, geophysics, and geology. Geology is really the study of the solid earth. It has many subdisciplines that I've listed here. You're all familiar with paleontology because I suspect you've all seen Jurassic Park and how important the history of life and fossils are for the study of the earth. Geologists are an interesting group of people. We're all scientists and we all love the earth. This is a slide which we used at one of our conventions to show you how the profession of geology is changing. The people in this slide on the left were geologists who attended a convention in 1924. You can see they're all wearing starched white shirts and ties. About 70 years later, our conventions consist mostly of much younger people, lots of women, and we're all wearing blue jeans. So things have gotten a lot more fun and less formal. So what is the Earth like? Well, the Earth is a very dynamic planet. And this diagram shows some of the processes going on, such as plate tectonics, where the continents are moving around over the mantle of the Earth, which is shown in orange. The Earth has a magnetic field that's generated by its iron core in the center, that's liquid iron and nickel. And many of these processes have really just been discovered in the last few decades. Now, one way we really study geology is to make geologic maps. Geologic maps, and this is the map I referred to in the introduction, it's color-coded to the age of the bedrock. It's as if we stripped all of the soil and forests off of the lower 48 states, and we had a geologist go paint the different ages of rocks in color. And this is a very important map to help understand the history of the Earth. Now, the color code is correlated to the geologic time scale. This is a time scale. The youngest rocks are in the left column, and the very youngest rocks, sediments which are being deposited today, are light colors, the light gray, tan, and yellow. And as we go down that column on the left, the rocks get older until we get to the Cretaceous and the Triassic, Jurassic, and Triassic. That's the age in which the dinosaurs lived. Then you continue in the center column. At the top, the blue is Permian age rocks. We all know about the Permian Basin in Texas, which is a very important oil-producing area. And we go down to the darker colors, the older rocks, which are in purple. And then finally, in the column on the right, we get to the bottom of the Paleozoic time period, about 544 million years ago. And that's where we start seeing the end of fossils. In other words, we find fossils in all the rocks younger than 544 million years. And then we go to the Precambrian. Those are the oldest rocks we find on Earth. They can go back to about 3.6 billion years old, and they tend to be the bright orange and red colors. So keep this in mind as we look at the geologic map. Well, where did geologic maps come from? They came from an English a civil engineer who in the late 1700s was digging canals in England to transport coal from coal mines. His name was William Smith, and he was considered one of the fathers of geology. He created the first geologic map, and this is a book that you might find in the library called The Map That Changed the World, and how important his understanding was to the birth of modern geology. So he was a canal digger. He started to observe as he dug canals throughout England and Scotland that he kept encountering similar fossils, but at different levels, in different layers of rock. And he concluded the fossils were the remains of ancient life and that they might actually be able to correlate the different layers of rock because of the age of the fossils seemed to indicate the age of the rock. Now, geology is all around us. This is a picture that I took in a parking lot in Austin, Texas. You can see the layers of rock, the gray and the black layers, and there's a fault on the side of this parking lot. And you can see in the center of the slide where the layers on the left have moved down relative to the layers on the right. Now, geologic time is a very important aspect of studying geology. This is geologic time represented in a circle, as if you're looking at the face of a clock. And it's color-coded, similar to the geologic column that we use to create the map. The oldest rocks are in the upper right portion of the clock. They're the reds and the purples, and those are the very old rocks. As you come around this clock face in the clockwise manner, and you get to the yellow rocks, we all of a sudden get to the rock age of 544 million years. And then the blue, the green, and the orange are the most recent rocks. And those are the ones we get to study the most because they are the most common rocks at the surface of at least the lower 48. Well, how old is the Earth? It's about 4.6 billion years old. But fossils are only about 544 million years. And that becomes a basis of a lot of our understanding of the Earth. Now, you've grown up in the age of dinosaurs because you've all seen Jurassic Park. I gave a talk at my granddaughter's kindergarten class, and it turned out I thought I was reading them a book about dinosaurs they'd be interested in, and they basically knew more than I did about dinosaurs. So this is a great thing that you young people are learning about the history of life because of the popularity that was caused by some of the Jurassic Park movies. A very interesting thing happened a few years ago, just a couple decades ago. A geologist discovered that there's probably a really good explanation of why the dinosaurs all of a sudden disappeared. And we believe the Earth was hit by an asteroid about 65 million years ago, and that impact of that asteroid put so much debris into the Earth's atmosphere it changed the climate. That geologist's name was Walter Alvarez, and this is a very interesting book you might want to read. T-Rex and the Crater of Doom is about what may have happened to end the age of the dinosaurs. Now, meteors impact the Earth all the time. Sometimes they're debris in space, just chunks of rock or iron. Sometimes they're comets. This happens to be one that was photographed over San Antonio, Texas in 2014. We think it was about 4 feet wide, weighed about 4,000 pounds, and it completely burned up before it landed on the Earth. But what happened to the dinosaurs? Well, the best estimate now is that a much larger meteorite or asteroid impacted the Earth 66 million years ago. It probably was on the order of 6 miles wide, and it had an impact that was equivalent to several hundred trillion tons of TNT. Mr. Alvarez, Dr. Alvarez, discovered reasons to believe this happened and was the end of the dinosaur era. But where did that meteorite or that asteroid hit? Well, we think it hit in Mexico on the Yucatan Peninsula, There's geological and geophysical evidence for that, and the picture on the right shows magnetic anomalies, and you can see the yellow circles. And we believe there was a major crater created there, but because the Earth has an atmosphere, the crater has been eroded away. Well, scientists are studying this to confirm the theory. And just a couple years ago, the Smithsonian Institute and a number of universities drilled a core hole just off the Yucatan Peninsula using an offshore drilling rig that's shown on the right here. And so they sampled the rocks as they drilled deep into the earth. The area of this impact site is called Chicxulub. That's named after a village in Mexico. And this is what we think it looked like after the asteroid hit. Big concentric circles on the left. And when the rig drilled a core hole into the center of this area, they found rocks which had been dramatically altered by high temperature and pressure. And one of the rocks is shown on the right. It's melted limestone and granite, much shallower than we would have expected it to occur. And we believe that's the outcome of the meteorite impact. Now, there are places where craters still exist that are billions of years old, even though the crater that we believe existed in Mexico is no longer visible. This is a picture of the moon, and these craters still exist. They look like they happened very recently, but they actually happened several billion years ago. So what's the difference? Well, the difference is the moon does not have an atmosphere. So the craters that form on the moon tend to exist relatively undisturbed for a very long period of time, whereas on the Earth, they're quickly eroded away. One of the key pieces of evidence Dr. Alvarez found was a recurring thin layer of rock, and this picture on the left shows what it looked like in an outcrop in Italy. There's a dark band of rock, very thin, just a few inches thick, that contains an unusual element called iridium. Iridium is not common on the Earth, but it is common in meteorites and asteroids in space. And so this was some of the evidence that there was a huge impact that put debris, which is rich in iridium, into the Earth's atmosphere. Now, the locations where we find this layer of rock are shown in the map on the right, the red dots. It's been found many places around the world. It always occurs at the same interval. There are examples of it here in Texas, and we think that is some of the primary evidence that the end of the life of the dinosaurs occurred because of this impact that put so much material into the atmosphere. So we'll go back to that geologic time scale. When did this impact probably happen? It probably happened at 65 to 66 million years ago. We call it the Cretaceous Tertiary boundary, or the KT boundary. The green arrow on the bar to the left shows where that occurs, and it's a very distinct change from the greenish rocks to the yellow rocks. We find dinosaur fossils below that layer, and then all the dinosaurs go away as we find rocks younger than that KT boundary line. So again, the other interesting thing here is we find fossils of different kinds of life going all the way back to 544 million years ago. And then we find very few fossils older than that, probably because animal life at that time, older than 544 million years, did not have shells or skeletons to be preserved. So now let's look at the map. We'll go to 4 different places where we can see very interesting geological relationships on the geologic map. So first we're going to go to the Snake River Plain near Yellowstone National Park. That's the area I referred to in Idaho. And this is a zoom in on just a piece of the geologic map. And what you can see here is the very light colored tan rocks, which are very young. And they form a strip going from the northeast to the southwest. And they are very close to Yellowstone National Park. Well, why are these young rocks here and appear to be at an angular relationship with the older rocks, which are more colorful, and it's because of recent volcanoes. It turns out the Earth's crust is moving slowly westward over a hotspot of magma. That's a similar process to what's going on in Hawaii, which I'll show you in a minute. But let's look at what it might look like underground if you were in the Yellowstone National Park area. Well, first of all, we're going to zoom in again on that map. The area with the red circle is where Yellowstone National Park is today. And of course, there's a lot of evidence of volcanic activity there because we have hot springs and geysers. The picture in the lower right is what it looks like from the space shuttle. The Snake River Plain is this area of light brown volcanic rock that's very young. And you can go visit it at both the Yellowstone National Park and at an area in Idaho that's a state park. Okay, let's look at what the underground might appear like if we could look inside the Earth. The top of this display is a map, and you can see where Yellowstone National Park is. And underneath, we believe there is a giant column of magma, as much as 2,500 degrees Fahrenheit. But the Earth's crust is sliding over this magma chamber or hotspot so that volcanoes, volcanic eruptions, appear to form this long strip of very young volcanic rock. Currently, the lava is underneath Yellowstone, but a few million years ago it was to the west. So this is a geological interpretation of the history of that area. Yellowstone has basically moved. So the area where the magma is reaching the surface gets older and older as we go to the southwest, and it appears it's been going on for at least 16 million years as the North American tectonic plate slides over that hotspot. This is a map of the area that's at one of the state parks. Actually, this is at Yellowstone National Park. And so the current location of the hotspot is Yellowstone Park, and that's the area in the center right with the red dots around it. So why don't we see a big volcanic crater at Yellowstone? Because it's been eroded away. 16 million years ago, the hotspot was way in the upper left corner of the map, and it will continue to move. So as I mentioned, the same process we think is going on in Hawaii. This is a diagram on the top center of the Hawaiian Islands. The islands we actually see are on the right side. They are volcanoes that happen to be tall enough to stick up above sea level. That's why they're islands, and we can go visit them. But again, the oceanic crust, the Earth's crust here is moving over a hotspot. And the diagram of how that's working is in the center bottom illustration. The magma chamber is red, labeled hotspot. And as the Earth's crust moves over that hotspot, volcanoes are formed. And there's a whole series of extinct volcanoes going to the northwest and become seamounts. They don't break the surface of the water, so they're not islands. It's very dramatic to see this. There's a picture of myself in the upper left in Hawaii at Kilauea, the current volcano that's erupting. And you can see the photographs on the right. What happens when the lava gets to the surface, it actually has caused damage to homes and roads. And in the bottom right, there's some guys playing golf and are about to have to move because there's lava coming towards them. Okay, let's go to the Grand Canyon National Park. Now, if we zoom in on our geologic map, which is the segment of which is in the upper left corner, we can see the geologic age of the rocks at the Grand Canyon. The rocks at the surface that you would be standing on if you go visit the Grand Canyon at its rim are Permian in age, they're blue. And as the Colorado River cuts deeper and deeper into the rocks, it starts exposing older and older rocks, layers of rocks. And that's why the colors change from blue to the lighter colors, and then finally the reds and oranges of very old rocks. This is what the Grand Canyon looks like from the rim, and so it's very, very visible to see the layers. A geologist who trained many of the Apollo astronauts had a great description of what we see in the Grand Canyon. And he told astronauts who were his students, and I have a quote here, "The Earth is a book waiting to be read. I'll teach you the language so that you can read the book you find when you land on the moon." And of course, that's what the astronauts did by going to the moon and collecting rocks on the moon. Here's another view of the Grand Canyon. And again, I've color coded the layers. The layer at the top is Permian, and it goes older and older as you go deeper and deeper into the canyon until we finally get to the place where the Cambrian sedimentary rocks sit on Precambrian, very old rocks. Now, right at the boundary between the pink bracket and the orange bracket is what we call an unconformity. Now, I had a chance to go to the Grand Canyon and actually touch that layer. So the rocks above my hand are Cambrian sandstones, about 525 million years old. Then there's a big gap of time. There's missing rock right where my hand is. And below my hand is Precambrian, very old rocks, 1,500 million years old. So there's nearly 1 billion years of erosion that has occurred at the surface I'm representing with my hand. Let's go to the Llano Uplift in central Texas. Again, this is a zoom in of the geologic map on the left. Very old rocks exposed in the center, the oranges and the pinks and reds, and that is granite, very old granite. Then younger rocks surround it, the greens and the oranges and yellows as we move to the southeast toward Houston and the Gulf Coast. The granite is very important economically because we make buildings out of the granite from the Llano Uplift. And I suspect many of you have been to the state capitol in Austin and seen the red granite building called the state capitol. Let's go to New England. Now, New England has a very interesting history because it was affected by the last ice age. And there's two very famous areas, Long Island, which is shown in tan on the lower left part of the map, and Cape Cod and Martha's Vineyard, which are in the upper right hand. And you can see here they are colored light tan, which means they're very young, but they're not volcanic lava. They are debris pushed down to this part of New England by the last glaciers in the last ice age. Well, the last ice age was really quite an event. It ended about 20,000 years ago. And this is a diagram I found that kind of helps you get a sense of scale. If the city of Chicago had existed 20,000 years ago, when the glaciers were advancing from the North Pole, this is what it might have looked like. Thousands of feet of glacial ice moving down from Canada, as tall as some of the tallest buildings in Chicago. Fortunately, Chicago wasn't there at the time. Now, we still have very cold weather in places like Chicago in the winter, and ice does form, but the glaciers are not there. The glaciers have all retreated into northern Canada, but we're just in between what may be a glacial advance and a glacial retreat. This is another diagram. If you look at the map on the left here, you can see the current coastline of New England, but we believe that the ice, when it was at its maximum extension into New England, 28 to 24,000 years ago, actually covered all of New England and went out into the ocean, out to the edge of the green area. Then the ice melted and went away, ending about 15,000 or 16,000 years ago. If you look at the image of New England using radar, this shows the great evidence of the glaciers All of these linear features you see from the top to the bottom are basically striations in the bedrock caused by the glaciers moving over the bedrock and scraping it and scratching it and leaving valleys. When you go to New England, I had a chance to do that. You can go to Acadia National Park in Maine, and you can see that there's giant boulders of granite, but they're not from that local area. They were actually brought there from about 50 miles to the north by the last glaciers. How did they get here? Well, here's an example of glaciers moving rocks in Alaska. This is an active glacier, one coming from the left, one coming from the right, and the glacier actually transports large boulders of rock. Everything that's black and the striated stripes of black on the glacier are rocks which are being transported as the ice moves. Now, one other thing I wanted to mention to you, plate tectonics, the theory of plate tectonics, that the continents actually move, is something we just discovered 30 or 40 years ago. And we think now all the continents were together in one very large continent. And the red area on this diagram is what things might have looked like about 284 million years ago. The equator would have been going through the center of this large landmass. And of course, the oceans have changed, and the world is about to experience major movement of the plates, of the tectonic plates, to form the world as we see it today. Now, there were some interesting critters around 284 million years ago. These are some of the fossils that we find that are from that time period. The one in the lower right is basically a centipede that was 16 inches wide and 6 feet long. So that's one of the very interesting things we study in geology, and particularly in paleontology. So if you wanted to find the oldest rocks that have ever been discovered by man, where would you go? Well, it turns out you would go to the moon. The moon was formed at the same time as the Earth, but as we said, it does not have an atmosphere, and so things are preserved. This is a picture of a geologist. His name was Harrison Schmitt, or Jack Schmitt, the only geologist to go to the moon. He's in a spacesuit in the lower left part of this picture, and he's sampling a giant boulder that has rolled down from the mountains near where Apollo 17 landed. And he's collecting rocks that date back almost to the formation of the solar system. What happens if you major in geology in college? Well, it's really kind of fun and interesting. These are some pictures of geology students. You do get to spend a lot of time outdoors, studying rocks and outcrops, going to national parks and so forth. And it's something that becomes a lifelong interest. When I say lifelong, I'm not kidding. This is a photograph of myself and some of my colleagues, most of whom are retired. And we were on a raft trip in the Grand Canyon to look at all the rocks that are exposed in the Grand Canyon. And we got to run the rapids in the raft that's in the right. And then we had geological lectures using a natural amphitheater formed by layers of rock on the left. Another interesting thing is that many of the astronauts, who, especially the current astronaut classes, who will probably include the people who are going to be the next astronauts to go to the moon, and possibly the astronauts who will be the first people on Mars. This is the most recent class of 12 astronauts. Of the 12, 2 of them are geoscientists. Jessica Watkins is on the right. She's a PhD geologist from UCLA. And Zena Cardman is a geologist in the front row on the left. And she is a PhD in geoscience from Penn State University. So this is really interesting. The career in geology opens up all kinds of exciting possibilities. The people who are interested in geology are often also interested in astronomy and space. And I just wanted to mention that to you. These are a couple photographs of events that have happened relatively recently. In 2012, we saw the planet Venus go in front of the sun. And then we had a partial eclipse in Houston in 2014. And then in August of 2017, there was a total eclipse of the sun visible in Wyoming and the northwestern United States. And there will be another eclipse in 2024 that we'll be able to see from Texas. So look around your world. This is an example of one of the things that got me originally interested in geology. This is a stone or rock in one of my neighbor's backyards in western New York State, and it's a fossil of a tree trunk from the Devonian period of geologic time. So we hope this has been a presentation that will get you interested in geoscience, maybe interested in getting one of the books I've mentioned, T-Rex and the Crater of Doom, or The Map That Changed the World, and might inspire some of you to pursue earth science as a career. So best of luck for you, and I hope this was of interest.
Well, I'm really happy to have been able to make this presentation to you today, and I'd like to encourage everybody to consider studying earth science and potentially majoring in geology or geophysics in college and get into a very fascinating career in studying the earth.